Good morning, students. In the today's class, we are going to see the filter with respect to the capacitive filter. We are going to see the operation of full wave rectifier as well as the bridge rectifier. In the previous class, we have seen the that capacitive filter operation with respect to half wave rectifier. In that, what is the construction part and what is the operation part we have seen. By using that, what is the ripple factor quantity is also analyzed, and depends upon that the same principle. We are going to see what happens if a capacitor is placed adjacent to the load resistance, and how it is going to vary the waveform with respect to full wave rectifier as well as the bridge rectifier. Okay, please tell me whether my screen is visible or not.
లో ఉన్నారు రైనా.
Is my screen visible? Students, is it my screen visible to you? Margo, is it visible? Is it visible? Anyone please respond. Nagajyoti? Students, tell me, is it visible? Is it visible to you? Is my screen visible? Okay. In today's class, in yesterday's class, we have seen this is the construction of a half wave rectifier with capacitor filter. The same construction, but we are placing one capacitor here across the load resistance RL. In the similar fashion, the cut-in point and cut-out point will take place in the output waveform. This cut-in point is the start of conduction, and cut-out point will give the end of conduction. To this end of conduction to the next start of conduction, up to the next start of conduction, we will consider the time as discharge time. This cut-in and cut-out points across these 2 points, I can consider that time as charge. Depends upon the. Am I audible, students?
Yes, sir.
Okay. Is the screen visible to you? Is my screen visible?
Yes.
This cut-in point and cut-out point, the conduction will take place. The charging of the capacitor will take place, and I am going to consider the time as charging time. From cut-out point to the next cut-in point, that means the next charging time, that I can consider that time as discharging time here. That is TC and TD. The entire operation is given by, if input voltage is greater than capacitance voltage, we can consider that diode is in forward bias condition. I can consider that time as charging time. If Vn is less than capacitor voltage, I can consider that condition as reverse bias condition, and I can take the time as discharging time. From that half wave rectifier, I am going to obtain the ripple factor as gamma is equal to 1 by 2 pi 1 by 2 root 3 f RLC. I am going to obtain. How it is going to obtain, we will see in this class. And this is the full wave rectifier and the bridge rectifier with capacitor filter. We are going to see operation of full wave rectifier only, operation of full wave rectifier with respect to the capacitor filter. And for our convenience, we are also drawn bridge rectifier circuit diagram along with the capacitor filter is drawn here. This is the construction part. One center tapped transformer, 2 diodes are used, D1 and D2, and load resistance Before this load resistance, I am placing one capacitor here. Across the capacitor, charging and discharging will take place, depends upon the positive half cycle as well as negative half cycle. In the similar fashion, for positive half cycle, here the step down transformer, 4 diodes are placed. One diagonal, for one diagonal this AC voltage is applied. For from another diagonal, I am going to take some output voltage here, from across the load resistance RL. This capacitor is placed before this load resistance RL. The charging and discharging of the capacitor will take place, depends upon the charging and discharging levels. Any two diodes, for the positive half cycle, D1 and D3 is going to be in the on state. For the negative half cycle, D2 and D4 are in the on state. That is the basic operation of full wave rectifier, and bridge rectifiers. By placing that capacitor, what happens we will see. Okay. During the first quarter of positive half cycle, the diode D1 is forward biased and diode D2 is reverse biased. Then capacitor charges up to the peak value of input voltage and tries to maintain this value. When input voltage falls below Vn is less than capacitor voltage. Both the diodes becomes, if Vn, this is the normal input waveform. This is 0 to pi, positive half cycle, pi to 2 pi, negative half cycle. Like that, I am taking one AC type of input signal. It can AC type of input signal is considered, and the output across the load resistance RL. That means this is because of diode D1. Let me. This is because of diode D1, and this is because of diode D2, and similarly this is because of diode D1, and this is because diode D2. Like that, the conduction will, the diode is going to be on position. Diode D1 is on in the positive half cycle, diode D2 is on in the negative half cycle, diode D1 is on in the positive half cycle, diode D2 is in negative half cycle, is going to be on. This process keeps on repeating. It consists of a center tapped full wave rectifier or bridge rectifier. Its capacitor is shown in figure. The inductor filter can also be used, but it is mainly used in heavy loads here. The capacitor is going to be charged from this point, to this point, to this point. Let it be, first point is cut-in point. The charging will take place across this diode. The charging of the charging will takes place to this level. The charging will takes place up to this level. The charging is going to be takes place. I am going to consider that it has charging time here, from cut-in point to the cutout point. That means in this region that diode is in forward bias condition. Beyond this point, beyond this, that means Vn input voltage is greater than capacitor voltage. Then only this diode D1 is in forward bias condition. The diode D1 is in forward bias condition. If Vn is less than Vc, if input voltage is less than Vc, then diode D1 and diode D2 both are in reverse bias condition. Means the conduction stops here. Both are in reverse bias condition, and discharging of the waveform is going to be takes place from this point onwards up to this point. From cut-in point to the cutout point, Vn is greater than Vc. Then if beyond this A point, then this it is keeps on decreasing here. The waveform is keeps on decreasing. That means Vn is less than Vc condition is taking place. Then diode D1 and D2 are in reverse bias condition. Here, that is the point given here. Capacitor charges through diode D1 from 0 to A. From 0 to A, this is in the charging position అనుకుంటున్నారు అన్నమాట. From 0 to, that is from 0 to A, it is charges. It is diode D1 is on and D2 is off. D2 is off. And from point beyond this point A, beyond this point A, from A to B, let us assume that it has A to B, A to B, those two diodes, these two diodes, that means Vin is less than Vc, then diode D1 and D2 are in reverse bias condition, and B to C, B2C ఏమవుద్ది మళ్ళీ B2C ఏమవుద్ది లోకేష్, B2C ఏమైంది మళ్ళీ కండిషను A to 0 to A, 0 to A conduction, charging of the diode will takes place, and that diode is in forward bias condition. From A to B, D1 and D2 are in off condition. అప్పుడు నెక్స్ట్ ఏమైంది B2C, C to D ఏమైంది చెప్పండి, B2C చెప్పాలి.
On condition, sir.
B2C, D2 is in on
On.
condition, D2 is in on condition and D1 is in off condition. C to D, D1 and D2 are both in off condition. In this way, this process repeats. మనకు కావాలంటే ఇక్కడ కూడా నెక్స్ట్ ఇక్కడ కూడా అట్లా 2 పాయింట్స్ పెట్టుకోవచ్చు అమ్మా, ఇక్కడ కూడా 2 పాయింట్స్ పెట్టుకొని ఆ ప్రాసెస్ రిపీట్ అయిందని కూడా ఎక్స్ప్లెయిన్ చేసుకోవచ్చు. ఫర్ అవర్ కన్వీనియన్స్ we have taken only A, B, C, D points అన్నమాట. Next, this process keeps on repeating like this. This is the first one is the charging time. From 0 to A is the from this cut-in point to the cutout point, that is the charging time. From this B to C is the A to B is the discharging time, that is TD. TC is the charging time, TD is the discharging time. From this diagram, you can clearly analyze the entire operation of the full wave rectifier with respect to the capacitor filter. Okay, this is brief explanation. From this waveforms we can explain the operation of a full wave rectifier. During first quarter positive half cycle, diode D1 is forward biased, diode D2 is reverse biased. Then capacitor charges up to peak value, then capacitor charges up to peak value of input voltage and tries to maintain this value. When input voltage falls below Vin or Vc, then Vin less than Vc up to until that is going to be on state until Vin less than Vc. Both the diodes becomes e point వరకు up to this point diode D1 is in on condition. Beyond this point both the diodes are in off condition. That is the point given here. Okay, thus capacitor starts discharging through load resistance RL. From this A to B, discharging of the capacitor may takes place here. Discharging of the capacitor may takes place. Then I can treat that both the diodes are in reverse bias condition here. It will continue till the input voltage exceeds capacitor voltage. ఇదే ప్రాసెస్ ఎప్పుడుదా కంటిన్యూ అయింది, విఎన్ వోల్టేజ్ లెస్ దాన్ కెపాసిటర్ వోల్టేజ్ అయింది కాబట్టి బోత్ ద డయోడ్స్ ఆర్ ఇన్ ఆఫ్ కండిషన్లో ఉన్నాయన్నమాట. అది మళ్ళీ నెక్స్ట్ అదే కండిషన్ ఎక్కడదా రిపీట్ అవుతుందంటే ఇన్పుట్ వోల్టేజ్ ఈజ్ గ్రేటర్ దాన్ కెపాసిటర్ వోల్టేజ్. కెపాసిటర్ దగ్గర ఉన్న వోల్టేజ్ కంటే కూడా ఇన్పుట్ వోల్టేజ్ ఎప్పుడైతే గ్రేటర్ అవుతుందో అప్పుడు మనకు మళ్ళీ అగైన్ కండక్షన్ స్టేట్లోకి వచ్చింది అనమాట. అది input voltage until this process repeats through the load resistance RL. It will continue until the input voltage exceeds capacitor voltage. Again during negative half cycle of input diode, D1 is reverse biased and D2 is forward biased. When in this condition input voltage exceeds, ఇక్కడ ఏం జరుగుతుంది, input voltage Vn exceeds the capacitor voltage. Here initially Vn exceeds the capacitor voltage, then again conduction exceeds the capacitor voltage, then capacitor starts charging again starts charging. The same procedure repeats for all the cycles. Here basic thing is Vn is greater than Vc, Vn is less than Vc. If Vn is greater than Vc means charging of the capacitor will take place. If Vn is less than Vc, discharging of the capacitor will takes place. In charging of the capacitor, diode is in forward bias condition. In discharging of the capacitor, diode is in reverse bias condition. That is the main points. The two main points you should remember. And this is the process. As load current increases, here the load current increases, then load resistance keeps on decreases. Discharging of capacitor will be greater here, resulting in more ripple and lower DC output voltage. Here discharging of the capacitor will takes place, resulting in more ripple. We are going to have some more ripple here, and the lower DC output voltage will takes place. And that ripple factor in the full wave rectifier is given by gamma is equal to 1 by 4 root 3 f RLC. This is the formula for ripple factor with respect to the full wave rectifier with the capacitor filter. This is the gamma term, ripple factor term. And the ripple factor can be decreased by increasing the value of filter capacitor value ni increase cheste I can increase this I can decrease this ripple factor. Filter capacitor value, by increasing the filter capacitor value, I can decrease this ripple factor. I can decrease the ripple factor by increasing this filter capacitor value. And next one is increasing the load resistance, increasing the RL. By increasing the load resistance, I can by increasing the load resistance I can decrease this ripple factor. By increasing the load resistance also I can decrease this ripple factor. But higher capacitancy means higher initial surge current, for which higher rating diode must be used. ఇప్పుడు మనం కెపాసిటర్ ఇంక్రీజ్ చేయగానే సరిపోదమ్మా. ఇది సైజ్ ఆఫ్ ది కెపాసిటర్ పెంచుతున్నాం అనుకోండి, ఆటోమేటికలీ దట్ మీన్స్ ద రేటింగ్ ఆఫ్ ది కెపాసిటర్ ఆల్సో ఇంక్రీజెస్. దట్ ఈస్ ద మీనింగ్ హియర్. కెపాసిటర్ సైజ్ పెరుగుతూ ఉంటే, ఇప్పుడు ఫర్ ఎగ్జాంపుల్ స్మాల్ కెపాసిటర్ ఇస్తారు, స్మాల్ కెపాసిటర్ ఇస్తే, let it be this is the capacitor, electrolytic type of capacitor. In order to, if we increase the size of the capacitor, that means the rating of the capacitor is also increased. That is the meaning of small capacitor, means its rating is small, power rating దీనికి తక్కువగా ఉంటుంది. అదే లార్జ్ కెపాసిటర్ ఉందనుకోండి, దీనికి ఈ లార్జ్ కెపాసిటర్కి పవర్ రేటింగ్ ఈజ్ హై అనమాట. అది దట్ ఈస్ ద మీనింగ్. That means if we are using, in order to decrease this ripple factor, if I am using the capacitor, large amount of capacitor, then we need to substitute large amount of diode also. డయోడ్ను కూడా అదే రేటింగ్ తగ్గట్లుగా డయోడ్ను కూడా ప్లేస్ చేసుకోవాలన్నమాట. అది the higher capacitor C means higher initial surge current will take place, for which higher rating of diode must be used. That is the meaning. Higher rating diode must be, higher rating capacitor use చేస్తే higher rating diode కూడా యూస్ చేయాలి. We are supposed to use higher rating diode also. That is the meaning here. As load resistance decreases, load current increases, but the ripple factor increases. Hence a filter is not suitable for variable loads. ఇప్పుడు లోడ్ని అట్లానే ఇంక్రీజ్ చేస్తున్నాం అనుకో, ఫర్ ఎగ్జాంపుల్ ఒక లోడ్ తీసుకున్నాం, లోడ్ రెసిస్టెన్స్ RL తీసుకున్నాం. Let it be that load resistance RL, we are using some fixed type of let it be some 100 ohms like that. I am using that fixed amount of time, fixed amount of load resistance RL I am using. If it is up to 2k like that, 2k like that, due to this variation the ripple factor may varies. Initially it is 0, initially it is 0. Up to 100 I am getting less amount of ripple factor here. Beyond this 100 I am keep on increasing this load resistance, ripple factor may increases here. So it is a variable resistor. By using some variable resistor, that ripple factor may increases here. So these variable loads are not at all useful for this application. It is useful, these variable loads are useful for the higher loads, therefore it is suitable for smaller loads only. This circuit is suitable for smaller loads only. For higher loads we need to use this variable resistors. For small applications we can use this fixed amount of resistors like that. ఏదైనా స్మాల్ అమౌంట్ ఆఫ్ రిపుల్ ఫ్యాక్టర్ని స్టేబుల్గా మెయింటైన్ చేసుకోవాలంటే స్మాలర్ లోడ్స్లో యూస్ చేసుకోవాలి. అదే రిపుల్ ఫ్యాక్టర్ వేరియేషన్ ఎక్కువగా లేకుండా స్టెబిలైజ్డ్గా యూస్ చేయాలంటే వీ నీడ్ టు యూస్ హైయర్ లోడ్స్ హియర్. వీ కెన్ యూస్ దేర్ ఇన్ దట్ అప్లికేషన్ వీ కెన్ యూస్ వేరియబుల్ రెసిస్టర్స్ ఆల్సో. దిస్ ఇస్ ద basic view. Okay. Just a minute. Ripple factor can be decreased by increasing the capacitor value by increasing the load resistance value. Load resistance value here for smaller applications we are supposed to use some fixed capacitor like that. For higher applications we can use this load resistance. Variable load resistance can be used. For this particular application, variable load resistance is not at all applicable. Okay. This is about the operation of full wave rectifier with respect to the capacitor filter. Next one is approximate analysis of capacitor input filter. In this we have seen this diagram already. In this diagram, maximum voltage is Vm, and the peak to peak voltage, ripple voltage, I am taking the ripple voltage as Vr here, and charging time there we have taken the charging time as Tc. Here we are taking the time as T1 here, T1. Here we are taking the discharging time as T2. This is the charging time. Just a minute. This is the charging time. T1 is the charging time. T2 is the discharging time. And please note this point. Please note this one derivation part. Please note down this derivation part. It is also very important. ఇది నోట్ చేసుకున్నామా? మీ నోట్స్ తీసుకోండి దానిలో ఈ డెరివేషన్ పార్ట్ నోట్ చేసుకోండి స్లోగా. Let us consider an output waveform for a full wave rectifier circuit using a capacitor input filter. This is the waveform we have obtained in the full wave rectifier here. That is the maximum. This is the output voltage. Maximum voltage is dotted line. Some dotted line, take that dotted line. Maximum voltage is Vm, and this is the charging time. Let it be that charging time is T1, and from this for our convenience, this is A, this is point A, and this is point B, and this is point C, and this is point D. In the previous case we have taken these points. A to B is the charging time, and B no, we have considered from 0 to, just a minute. This is A, this is B, this is B, this is C, this is D. Okay, this is A point, B point, C point, and D point. A to B, A to 0 to A, 0 to A, 0 to A, 0 to A is the charging time. Start of the charging. A to B is the charging time, and B to C is the discharging time. C to D is the charging time. Next D to E is the discharging time, like that. I am going to consider these points like this. This is the charging time, and this is the discharging time. Let capital T is the time period of AC input voltage. Capital T is the time period of AC input voltage. I am considering the time period as AC input voltage. Let it be the time period is this one. The time period is positive half cycle as well as negative half cycle. The time period is T. Capital T is the time period of AC input signal. T by 2 is the half of the time period. This time period, if I am considering this time period, this T by 2 is half of the time period. We are taking the time period as T by 2, that is half of the time period. T1 here, T1 time for which diode is conducting. Diode is conducting, or that is the charging time of the capacitor. That means this diode is in forward bias condition. This diode is in forward biased condition. This is this diode is conducting state. I can take that state as charging time of capacitor. This is the charging of capacitor may takes place. Charging of capacitor may takes place. I can consider this time as TC also. This is charging time. T1 is time for which diode is conducting here. T2 time for which diode is non-conducting. That means the discharging time of capacitor non-conducting. This is the discharging time. I can take this time as TD, discharging time TD. For our convenience, we are taking that time T1 and T2 in order to use that those 2 points in the derivation part. I am taking that time as T1 and T2, but literally those are TC and TD. During time T1, capacitor gets charged, and this process is quick. This charging time is very quick here, very quick. And during time T2, capacitor gets discharges through load resistance RL. This as time constant, this time constant, let it be time constant tau is equal to RC. Time constant is given by RC, both resistance term, product of resistance term and capacitor term. If with respect to the load resistance, I am converting that RC into load resistance RLC. RLC. I am considering the term as RLC here. Tau is equal to RC, and that with respect to load resistance is given as RLC. As time constant, RLC is very large here. The time constant is very large, and discharging process is very slow. Hence, this discharging time T2, is greater than T1 here. Discharging time, this is the discharging time. ఈ డిశ్చార్జింగ్ టైం ఇక్కడ నుంచి ఇక్కడ వరకు ఉంది కదమ్మా. దిస్ డిశ్చార్జింగ్ టైం T2 is greater than charging time, So I am taking that discharging time is very much greater than charging time here. That is given as T2 is greater than T1. This I am taking only this waveform. ఈ waveform మట్టుకే తీసుకుంటున్నానమ్మా. ఈ waveform, that waveform is indicated here. ఓన్లీ ఈ పీక్ టు ఇక్కడ నుంచి ఈ లెవెల్ వరకు తీసుకుంటున్నాను. ఆ వేవ్ ఫామ్ని కొంచెం ఎన్లార్జ్ చేసుకొని ఇట్లా చూసుకుంటున్నాం అనమాట. దట్ అప్రాక్సిమేషన్ వేవ్ ఫామ్ ఈస్ జస్ట్ లైక్ ఏ ట్రయాంగులర్ అప్రాక్సిమేషన్ ఆఫ్ రిపుల్ వోల్టేజ్లో తీసుకుంటున్నాం అనమాట. అదేంటి, ఈ మ్యాక్సిమం ఎంత ఉంది ఇక్కడ, మ్యాక్సిమం పీక్ ఈస్ విఆర్. maximum peak is VR. This is the VR here, and charging time this charging time is T1 and discharging time is T2, and total time period I am taking that time period 0 to with respect to the 0 to pi to 2 pi, like that. I am taking the time period as T by 2 here. Half of the time period, that time period is T by 2. ఇక్కడ maximum voltage ఎంత ఉంది, VR. Ripple voltage is VR. Half of that voltage is VR by 2. This is the triangular approximation of ripple voltage. After this one, ఇక్కడ వరకు అయిందమ్మా. ఇక్కడ వరకు చేశారా? ఇస్ ఇట్ ఓకే? ఇస్ ఇట్ ఫైన్? ఈ వేవ్ ఫామ్ నుంచి మనం డెడ్యూస్ చేసిన ఫ్యాక్టర్స్ అనమాట అన్ని. అవి మొత్తం నోట్ చేసుకున్నారా? ఎనీవన్ ప్లీజ్ రెస్పాండ్. ఇక్కడ వరకు అయిందా? షల్ ఐ మూవ్ ఆన్? రెస్పాండ్. ఇక్కడ వరకు ఓకే అమ్మా. ఇక్కడ వరకు రాసుకున్నారుగా. మెయిన్ పాయింట్ ఈస్ capital T is time period of AC input voltage, T by 2 is half of the time period, T1 is the charging time, T2 is the discharging time. T1 means charging time means conduction of the diode will take place. The diode is in forward bias condition. T2 means discharging time. The diode is in reverse bias condition. That is the discharging of the capacitor may takes place. The time period, I am taking the time period tau is equal to RC. That is given as tau is equal to RLC here. This discharging time is very much greater than charging time. To this point, we will move to the next slide. Let let VR be the peak to peak voltage of ripple voltage, which is assumed to be triangular shape. It is the VR is the peak to peak voltage of ripple voltage. It is just like a triangular waveform. Triangular waveform. Let VR be the peak to peak value of ripple voltage, which is assumed to be a triangular waveform, as shown in figure. Mathematically, RMS value of triangular waveform is given by VRMS is equal to VR by 2 root 3. This is the fixed value. This is the fixed value. We are considering that value here. That is the RMS value of triangular waveform is given by VR by 2 root 3. 2 root 3. And from that, just put this term aside. VRMS is equal to VR by 2 root 3. We are going to use this term final in the final state of this derivation part. During the time interval T2, during the time interval T2, capacitor C is discharging through the load resistance RL. I am considering the second time constant. The time constant is T2, that is discharging time. I am considering discharging time of the capacitor C. That charging last is the charge last is Q is equal to CVR. I am taking charge Q is equal to CVR. This is the C means capacitor, VR is the ripple factor. But we know that I is equal to dq by dt. Some flow of current will take place with respect to the charge and with respect to the time constant t. That is, variation is with respect to the charge and with respect to the time constant t. Time constant t, that is given by the formula I is equal to dq by dt. This is the basic equation. Current with respect to the charge and time constant t. And these time constant, I would like to know this value, what is the charge q, and I will with respect to get this charge q value, I am going to integrate the term here by rearranging these terms, and that q is equal to integral 0 to t by 2 I dt. These factors I into dt term integral. By knowing this, in order to get this value q value, I am supposed to ఈ derivative part ni normal term గా తీసుకురావాలంటే ఏం చేయాలి? Integral. We have to do the integration here. So I am making the term in order to obtain the charge term q value. I am integrating the term. I am integrating the current value term as with respect to the time. That is given by q is equal to integral 0 to t by 2 I dt. That is equal to, it is given by idc into dt. Idc, this is the I value idc, and t value, time period value is given as t2 here. T2 here, as integration gives average or dc value. By doing this integration, we are going to get the average or dc value that is given by idc into t2. That is equal to, we know this term, the charge q is also given by cvr. The charge last is given by q is equal to cvr. I am going to substitute, this is the q charge q value, this is the charge q value. I am going to equate these two terms. Then idc into t2 is equal to cvr. That implies vr is equal to idc into t2 by c. VR is equal to IDC into T2 by C. This is the term. Finally, VR, this ripple factor voltage VR is equal to IDC into T2 by C, where now we know that T1 is the charging time, T2 is the discharging time. That is equal to T by 2. T by 2. This is the half of the time period. This is the T1 is the charging time, T2 is the discharging time. This is the half of the time period. Entire time period తీసుకుంటే, ఈ టైం పీరియడ్ తీసుకుంటే, ఇది మొత్తం తీసుకుంటే టైం టీ అన్నమాట. ఇది మొత్తం అయితే టీ అవుతుంది. దానిలో హాఫ్ టర్మ్ తీసుకుంటున్నాం కాబట్టి టీ బై టూ దట్ ఈస్ గివెన్ యాజ్ దిస్ వన్. Normally T2 discharging time is very much greater than charging time. And next one, this T1 plus T2 is approximately equal to this discharging time is very much greater here. Discharging time is very much greater. Therefore, I am approximating here, that approximation is T2, that is equal to T by 2. We know that T is equal to 1 by f. We know the time period formula. Time period t is equal to 1 by f. Time period is reciprocal of frequency, and Vr is equal to, I'm considering that again I'm considering the term Vr. I'm considering this term Vr is equal to IDC T2 by C. T2 by C. IDC IDC T2 means it is approximately equal to T by 2. I am going to substitute this value here, T by 2 by C. That is equal to IDC by C into T means F1 by F. That is substituted here, 1 by 2F. That is equal to IDC by 2FC. IDC by 2FC. But IDC is equal to VDC by RL. We know this formula. But IDC is equal to VDC by RL from simple formula. Some simple formula, V is equal to IR. V is equal to IR formula. I am going to get this IDC is equal to VDC by RL. Hence, VR is equal to VDC. I am going to substitute here this IDC place low. I am going to substitute VDC by RL here. That is VR is equal to, again considering the term VR is equal to VDC by 2FC RL. 2FC RL is substituted here. That is the peak to peak ripple voltage. Thereafter, ripple factor is equal to, we know this ripple factor gamma. Ripple factor gamma is equal to basic formula Vrms by VDC or VAC by VDC. Vrms by VDC or VAC by VDC. This is the VRMS term. This is the VRMS term. Let it be this VR is the VRMS term. VRMS term. This is, I am substituting that VRMS term here, or VAC term, that is substituted here. VDC by 2 pi 2 FC RL. This term I am substituting here. After substituting that value by 2 root 3 by 2 root 3, that VDC value, this is the VDC value. Okay, initially we have written this term, that is VRMS is equal to VR by 2 root 3. That same term I am using here. VRMS is equal to VR by 2 root 3 into 1 by VDC. VRMS term I am using here. First term we have written, that first term is VR by 2 root 3. We have, after obtaining this VR term, finally I am substituting that VR term here. VRMS by VDC. This is the VRMS term. This is the VRMS term, VDC by 2FC RL by 2 root 3 into 1 by VDC. This VDC and this VDC get cancels, and finally gamma is equal to 1 by 4 root 3 F RLC. This is the final formula I am going to obtain. This is the final formula for full wave rectifier. Gamma is equal to 1 by 4 root 3 F RLC. In this way, we are supposed to derive the ripple factor in full wave rectifier. And for half wave rectifier, the same VR is given by VDC by FCRL. VDC by FCRL. Then ripple factor gamma is given by gamma is equal to VR of RMS by VDC. That value is given by VDC by FCRL by 2 root 3 into 1 by VDC. This VDC and this VDC get cancels, and finally 1 by 2 root 3 FRLC is going to be obtained for half wave rectifier. I am going to obtain this term. Okay, this is the term for half wave rectifier, that is 2 root 3. For full wave rectifier, that is 4 root 3. To this point, you finished this one, this derivation part. First initial ga time period తీసుకున్నామమ్మా. Initial ga time period T1 and T2, that is discharging time and charging time. T is the total time period from that diagram, this is the triangular waveform diagram. I am going to approximate the analysis here. Thereafter, mathematically, VRMS is equal to VR by 2 root 3 is analyzed. Thereafter, with respect to the charge Q, that is CVR, in terms of current, I is equal to dq by dt. By rearranging the terms, then in order to find out the charge Q term, I am going to integrate with respect to the current I and t, that is given by Q is equal to integral 0 to t I of I dt, that is given by IDC into dt. And we know the IDC value in terms in IDC value by equating these two terms, this charge Q and this charge Q is equated, then IDC into T2 is equal to C VR. That implies VR is equal to IDC T2 by C. This T1 plus T2 is equal to T by 2. T2 is very much greater than T1. Therefore, I am approximating the terms. Therefore, it is given T2 is equal to T by 2. T is given as, with respect to the frequency, is T is equal to 1 by F. After substituting those values here, VR is equal to IDC T2 by C, T2 by C, that is by substituting T2 value here, T by 2, and T is equal to 1 by F. That final term I am going to obtain is IDC by 2F. Thereafter, we know that IDC is equal to VDC by RL. Substituting the term here, VR is equal to VDC by 2FC RL. Initially, we know the VRMS is equal to VR by 2 root 3. That is substituted here. Basic ripple factor formula is VRMS by VDC value or VAC by VDC value. That is substituted here. Again, this term is going to be substituted, VDC by 2 FC RL by 2 root 3 into 1 by VDC. VDC get cancels, and finally I am going to obtain 1 by 4 root 3 FRL C. This is the ripple factor formula in the full wave rectifier. In the for half wave rectifier, in the denominator there is no two term here, no two term in the denominator, that is VDC by FCRL. By substituting the term with respect to the ripple factor, and finally I am going to obtain 1 by 2 root 3 FRL C for the half wave rectifier. These two terms are very important. You are supposed to write these we are supposed to derive these two terms in the examination also. After deriving these two terms, then only you are supposed to explain the operation of half wave rectifier as well as full wave rectifier and bridge rectifier. ఇది డిరైవ్ చేసిన తర్వాతే అది చెప్పాలమ్మా. యాక్చువల్గా నేను మీకు ఫస్ట్ ఆపరేషన్ తెలిసిన తర్వాత ఇది చెప్తే బాగుంటుందని నేను ఎట్లా చెప్పాను. యాక్చువల్గా in your examination you are supposed to derive this part first itself, and then explain the entire operation of half wave rectifier and full wave rectifier and bridge rectifier with respect to the capacitor filter. Okay. In the next session, we will see the comparison part of half wave rectifier, full wave rectifier, and bridge rectifier. Okay, students, please again derive this part and analyze yourself whether you are capable to do the entire derivation part or not. Okay. Just a minute.